There you go.
I have the batteries out of it. Okay, so today is the review for the exam. So everybody should have downloaded this, printed it out, and filled it out before you came today, so you have your questions. So what we'll do, the way I'll work this is I'll just go through it, say, you know, which ones do you want to look at? I'm not going to look at any that you don't have questions over. So, where do you want to start? We'll take the low bid. Any on the first page you want to see? What'd you say? I will, after we're done with class today, I will post the key to this online. So you can check the whole thing even if we didn't go over it. But I don't want to post it until people have a chance to try it without the key.
Number 5.
Number 5. Anybody need one before number 5?
On number 4.
What'd you say, number 1? Or number 4? Okay. And you said number 4 what?
Yeah. Number. Is it medium?
Okay, number 4 says, in human engineering and product design, it's important to consider the weights of people. It tells us that the weights of adult males in the U.S. have a mean of 173 and a standard deviation of 30. And it is skewed to the left. So I'm going to draw that. Skewed to the left means what? What's it look like? You did sound effects. Woo! That's good. So yeah, it goes like this, and the long tail points out to the left. So that is skewed to the left. Now, what do you know about the mean and the median, how they relate in a skewed distribution?
The median doesn't move as much as the mean.
The median does not move as much as the mean. We say the median is resistant to outliers, the mean is not resistant. So the outliers are on the low end for a skewed left distribution. So the mean will get pulled out into the tail a little bit. The median won't get pulled as much. So the median is going to sit more under the hump. So it'll be there. Now the mean, they tell us, is 173. So which value of these choices would work for the median? Hey, 188. 188 pounds is the only one of those that's bigger than 173. So the answer is A, 188. Now, I always get a little bit of argument from people, well, what about E? There's not enough information, because I don't have enough information to say it's 188 instead of 187. Right? And that's true, but don't get picky. Right? The point is, which side of the mean would the median fall on? So the answer is 188. Okay? Anything else off this first page? Excuse me.
I think someone said number 5. I was just
Number
wondering
5?
when the answer to that,
Okay, correlation and the regression line are they unrelated? No, they're closely related. Remember, the slope of the regression line has R in it as part of the part of the formula. Causal, not sure what that means. Correlation and regression line are causal? No. So it comes down to either resistant or non-resistant.
Non-resistant.
Non-resistant? Okay, and that means that an outlier can move it a lot. Remember we showed that, we had one point, we moved the line. If we made the guy with the really big shoes real short, it pulled the line down. So 1 point can affect it, that means it's non-resistant to outliers. Okay? How about page 2?
Number 9.
Number 9, okay? Number 9 says, in human engineering and product design, blah, blah, blah. That's the same thing I just read a minute ago. So it's the same distribution of adult males, only now they tell us it's symmetric and bell-shaped instead of skewed to the left. So let's fix the picture of it. It's symmetric and bell-shaped, centered at 173. What proportion of these weights is between 203 and 263? Well, where would I put 203 on this? Well, yeah, it'll be to the right of 173, but how far out?
One standard deviation.
One standard deviation, which is how far down the hill?
30.
What'd you say? I'm not looking for a number, but I always say one standard deviation is about halfway down the hill, right? So, about right there. So that's going to be 203, where that distance is 30 units, right? So if I go one more standard deviation, I'm at 233. And if I go one more beyond that, I'm at 263. And those are the two numbers that they quote, 203 and 263. So they want to know what proportion is in there. So I'm going to shade the region that I want the proportion for. Now a hint on how to work this problem is they gave me numbers that were both nice, clean multiples of the standard deviation. So what does that make you think of using? The empirical rule. Right? So this is an empirical rule problem. So, okay, now, if I'm going to use the empirical rule, let's start from scratch. In between plus and minus one standard deviation would be how much? 68. So 0.68 is in there. How much is not in there? 0.32. If 0.68 is in there, the rest of 1, or 100%, is not in there. So 0.32 is outside of those two lines. So how much of that is here? 0.16, which is 0.32 divided by 2. So same thing here. This whole distance from there out to infinity is 0.16. Right? And that's almost what I have shaded, only I have this little sliver here that's not shaded. So if I can figure out the area of that little sliver, I can subtract it off of 0.16, and I'll have my answer. Now right away you can pick the right answer without knowing the area, that, since it's multiple choice. What's the only one that is 0.16 minus a little bit? A, 0.1585. But let's go ahead and work it out. How do I find the area of that little sliver using the empirical rule? 99.7. In between 3 standard deviations above and 3 standard deviations below would be 99.7. So 0.997. So how much is not in there? Whatever's left. The leftover percent is 0.003. And how much of the leftover percent goes in that upper tail? That's not a trick question. How much of the leftover 32% went up here? Half of it. How much of the leftover 003 goes up there? Half of it. What's half of 003? 0015. So this area of that little sliver is 0015. So just a little more than 1/10 of 1% of the population would be out there above 263 pounds. So all I gotta do is subtract that off of 0.16, and I have my shaded region. So the shaded region is 0.16 minus 0.0015, which is 0.1585. Okay? Next question. No more? All right, we're done. Oh, I win. 16 and 17?
Yeah.
Anybody need one in between there? Okay. Oh, there's a bunch of fill in the blank stuff. So 16 says a blank is a display for 2 categorical variables. And the way it's worded, it makes it look like, well, there's one right answer, but there's actually a couple of different things you could put in there and it would be true. So it says a display. It does not say a graph. So in other places it says a graphical display. So two categorical variables I would accept side-by-side bar graph, because that is a display of two categorical variables. But that's not really the one they're looking for. They're looking for the one that's a table. What's that called? Contingency table. Or you could say a cross tabulation.
Then what's number 15? Because I didn't, I mean, it's like histogram or something.
Yeah. Two primary graphical displays for summarizing a categorical variable are and I would say bar chart, because if it's categorical we call it a bar chart, not a histogram, but I wouldn't get picky on that. I would say a bar chart and a pie chart, or that's probably the two that they're after. But there are other words you could put in there. A graphical display for two quantitative variables is called a scatter plot. That's a scatter plot. Okay? And then 17. 17 is a scatter plot. Okay, and what was the next question? Yeah.
Are we going to see this many multiple choice and fill in the blanks?
Not quite this many, no. What he asked was, will we have this many fill in the blank and multiple choice? When I do a review test, I don't worry about how long it's going to take you. It can take you all weekend for all I care, right? In fact, that's better. But I have to kind of limit things. So usually what happens is it's about a page to a page and a half of multiple choice, fill in the blank kind of stuff, and the rest is use your calculator, work things out, tell me what the equation of a line is, that kind of stuff. Okay. Oh, and another question I've already received from a few different people is, do I have to worry about all of the definitions or just the ones that were on the review exam? Well, that'd be nice, wouldn't it? No, you got to know them all, right? This is just intended to be a sample, kind of like this is a past exam that I gave over this, right? So I can't ask every single definition because there's room. So, but know them all because any of them are candidates, okay? And just because I don't ask you in this to draw a box plot doesn't mean I won't ask you to draw a box plot then, okay? I'll probably, on the real test, I'll probably have you draw something. It might be a scatter plot, it might be a box plot, it might be a histogram, it'll probably be one of those three things, but I probably only have you do one because they take a long time to do. So you'll do some kind of a graph by hand, but then the rest of it I'll give you a picture and ask you to interpret. Okay, what's the next question?
Twenty-two.
22?
Yeah.
I'm the only one asking questions.
Well, then somebody needs to. Sometimes you know what that means, is you're the only one that actually got it filled out in advance. I hope that's not the case, but you said 22,
A, C, and E.
okay? I've gotten a few questions outside of class over 21, so let me mention that real quick. This just gives you a set of 8 data points and asks you to find the mean and the standard deviation. So what's the strategy there? Put those 8 things in a list and then do
One bar stat.
1 bar stats. A lot of people, and this will happen on the exam, so look around the room and you'll see 1 or 2 people that'll do this on the exam. They'll compute the mean by saying 1.53 plus 1.5 plus ... divided by 8, and they'll get the mean correct. And then when it comes time for standard deviation, like, oh God, I don't know how to do that. If you just put it in a list and do 1 bar stats, it'll give you the mean and the standard deviation just all in one. Okay. If I ask you to do a box plot of this data, then 1 bar stats gives you the 5-number summary that you're going to need. The min, the quartiles, all that stuff.
What comes up on the calculator, there's one that's S and there's one that's a little whistle looking one. Which one do we use?
I've never heard it called that before. She said there's one on the calculator that's S sub x, and there's one that's a whistle looking thing. And it does look like a whistle. I never thought of that before. This one is the population standard deviation, which we won't use.
Okay.
This one is the sample standard deviation, and that one we will use. Okay? So you can just ignore that. Mariana,
Can you work number 21?
can I work number 21?
Would you work
I'll give the answers.
21? I mean, I'm just a little confused on the calculator part.
Okay. Let me. Let me get my calculator up here. I have data already stored in my calculator simulator, which is the problem number 25. So I don't want to erase that. So I'm going to put this data into L3, so I get away from those others. It came up here in the list editor because that's the last place I left it. So everybody knows how to get there, right? So let's go over to L3 and let's put those in there. Now I can't see the data and my calculator at the same time. So somebody just read me off those values. Yeah, I'm putting them in L3. You can put them in L1 if you want. But I'm putting them in L3 because I don't want to erase what's in L1 and L2. So read me off those 8 values.
1.53.
0.53.
No, 1.53.
Oh, 1.53. 1.53.
1.50.
1.50.
1.37.
1.37.
1.51.
1.85.
No, 51.
Are you trying to confuse me? Is this working?
1.55.
Okay.
1.42. 1.41. 1.48.
Okay, that's all 8 of them? Okay, so what do we say the next strategy is? Mariana? Push the stat button, then go over to calc. So I need to arrow over 1. And then one of our stats is what's highlighted because it's top of the list. So you just press enter. And I didn't clear the screen from before, so I got a bunch of garbage there. But down at the bottom it says one var stats and then it's blinking. So I need to tell it what list. And my list was L3, but you can put in whatever yours is. So I'm going to hit second function L3 and press enter. And that gives me the mean X bar is 1.47125. And the standard deviation is what?
0.064.
0.0640.
How many decimals do you know on that one?
I knew that question was going to be next. And that's a good question. How many decimal places will I require? I require at least 1 more than the original data has. The original data has 2, right? So you would need to keep at least 3. If you keep 3, you'll get full credit. If you keep 8, full credit. I'm not going to be like the online homework and penalize you if you give too much accuracy. But too little accuracy, that can be a problem.
So at least 1 more.
At least 1 more than what is present in the original data. Joy?
Yeah, I kind of want to backtrack just a second.
That's not allowed.
Yeah.
I'm just kidding.
But now I don't remember what I was going to do because I was listening to you.
I have that effect on me.
I'll come back when I remember what it was.
Okay.
Oh wait, I remember now. The stem and leaf plot on there, or that we had to do.
Yeah, let me get back to that.
How do you do it with decimals? I know
well-
that it's the 1 and then the number.
Yeah, the
On the
stem
other
and leaf
side.
plot, you always get to choose what your stem is going to be and what your leaf's going to be. So you look for something that's a natural kind of break point, and here it's the decimal
Okay.
point. So I'll make the stem the ones place, and I'll make the leaves the
So-
tenths.
So just by labeling them
Yeah.
and then put them, okay.
Yeah, and the way the software does it is it doesn't label them like that. It just puts some kind of cryptic message down below that it's whatever. But
That's
and
fine.
on this one, I do want to go a little bit further with it. If I let the stem be the ones place, I'm only going to have 3 stems because I got ones, I got twos, and I have a single number that's 3.0. So rather than have like a histogram with only 3 bars, you can split them up. Remember doing this? And I don't need the second 3 because there's only one value that's a 3, and it's a 0, 3.0. And then I'll put in, like, the first number is 1.4, so that would go right there. And then you just read it as 1.4 because it's ones and tenths.
Do they have to come on order from?
They do. That's a great question. She said, do they have to go in order once they're on the leaf? And yes, they do. And if you look at the twos, I think it's the twos that end up having to be reordered. The ones do also? Yeah, they do. So the ones you'd go 5, 7, 5, 8, right? Going across that top row. 5, 7, 5, 8. Yeah. So then you'd go ahead and make it all out and then just erase or draw another version of it and rearrange and make this go 5, 7, 8. They do need to be in order.
Why
Yep.
would you put like 2 values for 1 and 2 values for 2?
So that I have 6 or 5 bars instead of 3 bars. It's just a way of changing my interval width.
And it's 1 to 4 and 5 to 9.
Yeah, 0 to 4.
0.
So on the first one, it's 0 to 4, and then 5 to 9 each time. Okay?
Are we gonna have more room than that to draw it?
What's that?
Are we gonna have more room than that to draw it on the exam?
Yeah, that's another thing. When I do a practice exam, I don't worry about whether you have to put your answers on an extra sheet of paper or not. But on the exam, I give plenty of room because I don't want to collect a whole bunch of other pieces of paper. So you'll have plenty of room. And you'll have room to do all of your scratch work too, so you don't need extra scratch paper. How about 22? Is that the one you asked about a long time ago? Okay. 22 talks about acid rain and sulfur dioxide emissions in 47 of the states. And then it asks a series of questions about this histogram. So I'm going to scroll up so that we can see the questions and the whole histogram. Part A says, identify the intervals of emission rates used for the plot. There's not a whole lot there that you have to do. Here it never tells us where the boundaries go, but I would be a little more careful than that. I would say something like where the boundary goes in the bar to its right. So this one would go 0.5 to less than 1.0. And that's the way you would say the intervals. 0 to less than 0.5. 0.5 to less than 1. 1 to less than 1.5. And then it's okay to say ... You don't have to go all the way to 5 doing that. Okay? Part B, describe the shape of the distribution. It might help if I get into the light, I guess. Describe the shape of that distribution. Skewed to the right. Don't say bell-shaped. You'll miss points. It has a longer tail off this side than it does over here. And notice there's a natural wall at 0. You can't have emissions that are negative. Next one says, what information can you get from the dot plot or stem and leaf plot of these data that you cannot get from this plot?
Individual values.
Exactly. The individual data points are all there on the stem and leaf plot. But here, I don't know, there's 5 states that had emissions between 0 and 0.5, but I don't know what those emissions were. I just know they were somewhere between 0 and 0.5. Stem and leaf plot gives you that. D says, what % of the 47 states were above 3? How do I do that?
find the standard deviation and stuff like that.
No?
You don't have to.
And that's actually a common mistake for a question like that on this exam, is to go to the empirical rule and just do it based on empirical rule. But you can't do that here because I don't give you the mean and standard deviation. So all you're doing is counting from the picture. How many states were between 3 and 3.5? One. Let me raise this up so I can write on it. There's 1 in that bar. How many are in this bar? 3, and 1 and 1. So a total of 6 states
Out of 47.
out of the 47
13%.
are greater than 3. And that as a decimal, does anybody have that? It's 0.12 something, but I don't remember the 765. And again, when you're doing percents,
4.8%.
then 1 decimal place on a percent is plenty, or 3 decimal places on a proportion. So I would call this 12.8%. Okay? Last question, this histogram shows frequencies. If you were to construct a histogram using percentages for each interval, how, if at all, would the shape of the histogram change? So rather than draw this bar up to 5, I'd take it up to whatever percent 5 out of 47 is. Would it change the shape? Nope, it wouldn't. Not at all. The only thing that changes is the labeling on this y-axis. Everything else would stay looking the same. Okay? Okay, that's a good question to begin with, because I guarantee you will have a question like this on the exam. This is, I don't know if I can do that. Well, we can almost see it all. I like to be able to write on there. This is a contingency table. This is old data. This is not data from this semester, but the idea is the same. This column of the table is smokers, no, and yes, and then exercisers, no, and yes. So you have numbers in the table, then you have the margins of the table, and then you're asked different probability statements. A says, what is the probability that a randomly selected person from this table is a non-smoker? So how many people in this table are non-smokers? 415. It's a marginal total. That statement doesn't say anything about exercise, so you ignore exercise, you go all the way to the total. So this is a row total. So this one's 415 out of 505. And you can leave it like that. There's no reason that you need to write it as a decimal. Lost a brand new marker. Must have left it in the other room. What is the probability that a randomly selected person is either a non-smoker or an exerciser? What does the word or mean? Add. That's addition. So I'm going to write in this space here. Probability that a randomly selected person is either a non-smoker or an exerciser. That's the probability of being a non-smoker plus the probability of an exerciser. And then we subtract something off. What do you subtract off? The people that are both. Because they get double counted. There's a certain number of people who get counted as non-smokers and they get counted as exercisers. So you have to subtract them off because they've been double counted. So add them in twice, subtract them off once, and you're covered. So that's the probability of ones that are both. So and EX. Okay, so from the table, I have probability of non-smoker. That's the one we already did. That's 415 out of 505. Probability of exercisers. Well, this column are the exercisers. So I've got 247 total exercisers. Then I subtract off people who meet both conditions. And how many people are that? 222. So then, pardon me while I try to do two things at once. Tanner, I've been carrying this around, and you never remember to ask me, and I never remember to give it to you. So I need to subtract off 222 from there. Now I'm adding or subtracting three fractions. How do you add fractions? Common denominator, and then just add across the tops. Well, they're already a common denominator, so I need 415 plus 247 minus 222. What do you get?
440.
440 out of 505. As a decimal, you just take 440, divide by 505. You don't need to do that. I'd give you full credit for that answer. But as a decimal, what is it? 0.87. Okay? So that's an OR statement. Part C says, what's the probability that a randomly selected person from this table is a non-smoker given they exercise? What's that word given mean?
And
It-
then divided by.
It's a conditional, right? So probability that a non-smoker given they exercise. Probability of non-smoker given they exercise. Now I heard somebody starting to say that the rule for conditional probabilities, and I'm going to go ahead and write it down, but in this particular case you don't have to go this all out. Divided by the probability of what?
The given.
The one that you're given. But in this case, dividing probabilities is just the same as dividing numbers, because if you make this a probability, it's divided by 505, and the bottom's divided by 505, so they cancel. So all I got to do, I don't have to worry about the probabilities. I can just say, well, it's the number who are both divided by the number of exercisers. So this is a contingency table problem, so you can get those numbers just by looking at the contingency table. And we did this in the first exam, only we didn't call them conditional probabilities, we called them conditional proportions. That's the same thing. So out of those who exercised, there's 247. How many both were non-exercisers and non-smokers and exercisers? 222. So it's 222 out of 247. Okay, somebody give me that as a decimal. 0.8987. Okay? Part D says, would you say that being a non-smoker and being an exerciser are independent events? Show why using probabilities. Well, this is one of those checks for independence. And you have several choices there you could do, and any of them will get you full credit. So what do you want to use as a check?
Probabilities equal 1? Or would that matter for any?
No, you wouldn't use that here. That's to check that it's a probability distribution. Any ideas?
B given A should equal P of B.
Okay, so NS given EX should equal probability of NS without conditioning, right? That's this. Probability of A is equal to the probability of A given B if they're independent. Well, we've done both of these. We just did this one, and we did probability of NS right here. So that's 415 out of 505. Give me that as a decimal. .82. Okay. Are they the same? No, they're not the same. But remember, with real data, they're never going to be exactly the same. So what you have to do is say, well, are they about the same or are they pretty far apart?
Pretty far apart.
I'd say they're pretty far apart. That's an 8 percentage point difference there. But what makes it even more telling, I think, is to do the condition on the non-exercisers. So EXC, exercise complement. This says what proportion of exercisers don't smoke? And that's about 90% of them. Now I'll say what proportion of non-exercisers don't smoke? And that, from the table, probability of non-smoking given they were a non-exerciser is 193 out of 258. Somebody give me that as a decimal. 0.75. And now you compare these two numbers, and you see they're pretty different. So the proportion of exercisers who don't smoke is about 90%. The proportion of non-exercisers who don't smoke is 75%. That's a big difference. Therefore, independent or not?
No.
You said no, Morgan? Which is it? Are they independent or not? They are independent? They are not independent. They are not independent. If they're the same, then it doesn't matter what you condition on. You should get the same number, right? If they're independent, then conditioning on this shouldn't matter.
So you have to do both to prove it, or can you just do one or the other?
You could do one or the other.
Okay.
But it's if these look kind of close and it's a little bit of a gray area, then you go this one because it makes it more obvious,
Okay.
right? You could also do, as another check, you could do the AND statement, the multiplication rule. Check and see if the AND is equal to probability of NS times the probability of EX. If they're independent, those should be the same. If they're dependent, you'll get different numbers. And the magnitude of the difference there will be about the same as it was here.
Which would you say is generally better to use?
I like this. I like condition on one part of it, condition on the complement of that, and see how those numbers compare. Because that's really how you would do it intuitively. You know, well, is smoking independent of exercising? Well, I don't know. What percent of exercisers smoke? What percent of non-exercisers smoke? And I'd compare those two numbers. That's what seems to make the most sense. Okay, next question.
Number 14.
Number 14. Okay. There it is. The participants in a homeowner survey were questioned about their educational background and marital status. Of the 400 participants, 240 had college degrees, 108 were single, and 100 were single college graduates. The probability that a participant in this homeowner survey is married and has a college degree is. Now, here's a little bit of advice. Fatherly advice. When you read a problem like that, it's okay if you have this reaction. I can't do it. Right? You might get that moment of panic where you get that test anxiety thing going and you think, oh God, I have no idea how to work this problem. It's okay, just take a deep breath, go back to the beginning, start reading it again, only this time start putting the information that they give you down in pieces and try to organize it. And then it'll become, oh, I see what to do now. Because when you first read it, it's overwhelming. There's just too many numbers, too many ifs and thens and all that in there, right? So in a probability problem like this, you've got really 3 different ways that we've learned to organize information. One is a contingency table, one is a tree diagram, and one is a Venn diagram. And you could do any one of those 3 here and make it work. But this one lends itself to one of those more than the others, right? What does this look like it might be good for? I heard all three. What I think of as a contingency table, because I think, okay, I got marriage status and I got college graduate status, and then I'm going to cross-tabulate them, right? But you could use a tree diagram, you could use a Venn diagram. Really, a contingency table is just a Venn diagram. It's just done in squares and blocks instead of circles. So I'm going to go married, yes, no, and I'm going to go college graduate, yes, no. And there's my contingency table. Now, a common mistake on setting up a contingency table, this is very common. People will do this. Married, college, yes, no. What's wrong with that?
Yes,
You're not
no, that
crossing.
makes sense.
It doesn't cross-tabulate them all. I can fill in the numbers because I know how many were married, I know how many were not married, I know how many were college graduates, and so on, but it doesn't cross-tabulate. So this isn't wrong, it just won't help. What you need to do is cross-tabulate. So you need one variable as rows and one variable as columns, and you have two variables under consideration, marital status and college status. Okay, so now we just start filling in numbers. Of the 400 participants, okay, now where does the 400 go? That's the grand total down here in the corner. Next thing it says, 240 had college degrees.
The total of college.
The total of yes to college. So that's down here, 240. 108 were single.
Married, no.
Married, no. It's again, so far everything they've given us has been a total. Either the grand total or a marginal total column or row. They have to give us at least one number that goes in the table or we can't solve it. And that's coming up. And 100 were single college graduates. So that's an and statement. Even though they didn't use the word and, they were single and they were a college graduate. So and go in the table because they have to meet two conditions at the same time. So where does it go? A single college graduate. That's a no for married and a yes for college. So that's going to be 100. Right? Now, once we have that much, we can fill in the whole rest of the table just by subtraction. Right? But you don't really need all of it to solve this problem. It says, the question they ask then is, the probability that a participant in this survey is married and has a college degree. Well, that's this cell. Married, yes, and college degree, yes. I need that number.
140.
140. And you get it by subtraction. If 240 total and 100 of them are here, 140 are there. So the answer is 140 divided by 400. I was waiting to see if somebody would say 240. 240 would be conditional probability. But this isn't conditional, it's just an and statement, so it's over the grand total. So 140 over 400, and what is that as a decimal? It's multiple choice. 0.35, which so it's option D, 0.35. These other distractor options are going to be things like the conditional probability, going each of the two directions, and things like that. Okay? Next question. 24?
I want to do the last part of 23 too.
Yeah, actually, I have
Yeah,
that too.
C.
24, or 23.
Okay. We'll do 23 and we'll do it all, and then we'll do all of 24. Let me scroll just a little bit more and we'll be able to see part C above that band. There we go. Okay, this is a ball bearing question. The process of manufacturing ball bearing results in weights that are approximately normal